Hi and welcome to this video.
Who the hell are you?
My name is Jan-Hendrik and in this video I would like to cover the topic measures of correlation. Let's see what I planned for this video. The first thing I would like to show is to how calculate the covariance. The covariance is hardly interpretable, nevertheless it's the basic for all further calculations. Then I would like to go into Pearson's correlation coefficient and into Spearman's rank correlation coefficient. First, we're going to do this in R. Later on, we're going to do the theory and the math behind. So, let's see why that is important. Here on our right button side, we see what is typically shown in each and every journal article. It's a correlation matrix where all metric variables are shown against all other metric variables. Of course, on the main diagonal, we see the 1 since each variable correlates with itself perfectly. Accordingly, we see a 1 here. All that, of course, comes out of typical statistics software. Here we see a German version of Gretel. Nevertheless, we see also in statistic software suites that we have those correlation matrices. For today's video, I prepared the following data. I will use some income data that we already know from other videos, just like here. And we have a very small population of only 9 persons, and they have an income of 22,000 euro, 24,000, 25,000, up to 105,000 euros. Additionally, we're going to observe the wealth of these persons. So this person owns some 20,000 euro. This one only 15,000, this one 13,000, this one 24, and the rich guy on our right hand side has some 180,000 euro. And just to show that a correlation matrix is possible and not only a correlation, we add the age of those persons, like 23, 40, and 32, and so on and so forth, years. Well, let's switch to our studio and I show you how that is going to be calculated.
And now for something completely different.
Now, I have arrived in our studio and this time I have prepared a little because it's too boring to show how I type in all that data. What have I prepared? I just opened a new script window, just like here. I don't click on this again. I gave all that a beautiful headline, measures of correlations, and I already prepared a data section. So what is performed in this data section? I define 3 vectors. The first one is the vector income. The name of this vector is freely chosen. I could also call it Marlboro or Harley Davidson or whatsoever, but this vector is called vector underscore income. We are going to assign some data to this vector. That's why I prepared this little arrow with a smaller than and minus. And we use the combine, the C command, which stands for combine, to combine this vector out of 22,000, 24,000, 25,000 up to 105,000. And that's the income of those 9 persons. I'm going to run this line using Control and Enter. And on the right hand side, we see that there is now the vector income in our environment. It's a numerical vector with 1 to 9 elements. The same with wealth and the same with age. Accordingly, we now see all 3 vectors. And with a line 9, which continues, just like here, which continues in the next and even the next line, all those 3 vectors are going to be put into one data frame. So here the df data frame is defined. df stands for data frame, of course, df underscore data. Again, some data is assigned to it, and we use the data frame command to combine those three vectors, and I give them new names like income, like wealth here, and like age. I run this line too, and now we see here that we have a data frame with 9 observations, because it's 9 persons, in 3 variables, and we can take a look at those variables. It's income, wealth, and age now, and all 3 of them are numeric. Now, the first thing I would like to show is the covariance. So we apply the command cov, or cov, like covariance, and we have to hand over the data frame, df data, and that's already it. I run this line, and I get the covariance matrix here. The covariance is in euro squared. Euro squared is hardly interpretable. Nevertheless, it's the basis, and we need to cover that too, of course. What is more interesting to us, of course, is Pearson's correlation coefficient. And we can calculate that one using the core command. And we have to hand over df data again. And I run this line, and here is the typical correlation matrix using Pearson's correlation coefficients. Here again we see on the main diagonal the 1, because each variable correlated with itself perfectly correlates positively. Accordingly, we see a positive 1. The correlation coefficients, they are all normed or normalized in the interval between -1, perfectly negatively correlated, up to 1, perfectly positive correlated. To get all other correlation coefficients, like Spearman's, or it's Spearman, it's a rank correlation coefficient, we can hand over additionally to the core command and additionally to the data frame, we can hand over a method that defines that Spearman shall be used here. And if I run this line, I got slightly different. Let's see. So Pearson was 0.946, and now we have 0.933. It's rank correlated here. Rank correlations are a beautiful thing to do if we want to get rid of outlier problems, because they are more robust to outliers. Well, there's a third one that I'm not going to cover in this video too much. Nevertheless, I would like to show. It's Kendall's tau. And of course, I can reuse this code and copy it here and just replace Spearman by Kendall and run this, and here are the numbers for Kendall's tau. Well, of course, this is only very basic functionality. In most journal articles, we see also that there are test performs on the correlation coefficients. And we can do that too, but not in our base. We will need to apply a package to this. So what package could we use here? We're going to use hmisc. So tests on correlation coefficients, just a little more space. And yeah. If not yet done, you need to use install.packages command. And the name of the package is hmisc, like miscellaneous. And of course you can run the install.packages command just like this, but since you have to do it only once in the lifetime of your computer or your R installation, you can hide it then in a command. If you share your code with your colleagues or students or whomsoever, it is very helpful to them to see, oh, there's a package installed. I just forget the second quotation marks here. It's just helpful to them to see that there has to be a package installed, otherwise the code wouldn't run and they wouldn't notice. Of course, since this package is already installed on my computer, I'm not going to redo this. Then of course we need the library command. This has to be done each time, and it's hmisc. I'm going to run this package. Oh, seemingly there had to be something reinstalled. Nevertheless, it's done now. And now we can perform those tests. But what's the reason to do those tests? We want to know if there is a significant correlation. So we can always calculate something, but can we really rely on those numbers, or are those numbers randomly induced? Are those numbers pure random? And accordingly, we have a null hypothesis. Let's put it like this. So the null hypothesis is that the correlation coefficient that we're going to calculate does not significantly differ from 0, or deviate, let's say differ from 0. Of course, there is an alternative hypothesis, and this is what we really want. So alternative. The alternative hypothesis, of course, is that the correlation coefficient so if this test supports our alternative hypothesis, the correlation coefficient is to a very high probability not randomly based. So the variables do interact. Okay, how can we do that? Now we apply the rcore command. The rcore command comes with the hmisc package. It's not implemented in RBase, and unfortunately the rcore package wants to have a matrix handed over and not a data frame. Accordingly, we have to turn the data frame into a matrix. We can do this with the type conversion as matrix. And now we hand over the df data frame, and that's already it. And we can run it, and we get some output. Let's take a look at this output. This output is made of, first, a correlation matrix that we already know, more or less. If I scroll up, here we had the Pearson correlation matrix, and these are mainly the same numbers. Let's keep that in mind: 0.946, 0.932. Of course, they are now rounded, but these are mainly the same numbers. Additionally to this matrix, we get this beautiful matrix that has or shows us the p-values. And the p-values, as you know, will be used to check out if the test has a significant outcome or not. So check the significance of the correlation coefficient. And typically, we compare those p-values with some what's the word in English? Some threshold, some significance threshold. Typically it is 5% or 0.05. And if this p-value falls below this threshold, we speak of a significant or even highly significant result. Let's see. So income and wealth do correlate significantly, because this number, this p-value, is far below 0.05 or even 0.01, so it's even under 1%. It's pretty low here. So we speak of a significant result. Significant means that the alternative hypothesis is supported here. So always if the p-value falls below our significance threshold, let's say 5%, we support the alternative hypothesis and we reject the null hypothesis. Vice versa, if the p-value is above that threshold, we do not reject the null hypothesis and we stick with it, so that would be not significant. But since it is now very low, we support the alternative hypothesis. Or in other words, the probability that this result is randomly induced is very low. Accordingly, we support the hypothesis that these two variables interact, that they are correlated. Of course, it would be nice to have those values individually. So what we can do is to save the result in some kind of model variable. I just do it like this. I give it a mod-like model, and it's a correlation. And of course, we assign this data to the model variable. And now we see here on the right-hand side that we have a list of 3 items, and we can take a look at those items. Here we see the R, so the correlation coefficient, the N, that should be the number of observations, and the capital letter, this is important, the P values. And that tells us that we can use this mod core list, and we can apply, just like a DataFrame, but it's a list, the $sign, and we can now choose the P and run this line, and we only get the P values, and now they are not rounded. Now we see the full number of digits of those p-values. Of course, we can do the same, and this is what I should have done first normally. We can do the same with a small cap r. Don't forget small cap r here and large cap p. So small cap r, and here are the correlation coefficients for Pearson correlations. Of course, we can do the same, and I just do this. I copy the code and put it here. But now I add an S, because we are now going to do Spearman correlation. And the parameter that we have to set now is type. It's not method anymore. Now it's type, because our core is a different command. Method now is Spearman. And I run this one. And let's take a look. Yeah, we already know those numbers, but what we don't yet know are the p-values, but they are still, all of them, very, very small. So they're all significant if we apply this significance threshold of 5%. Well, that was it in our studio. Now let us have a look at the theory and the math behind those correlation coefficients. For understanding the theory and the math behind correlation coefficients, it always makes sense to visualize the data. And here we see a scatter plot. While in the last videos we only had strip plots because we only took a look at one variable at a time, we now look at 2 metric variables that are income and wealth. Accordingly, we use this scatter plot to visualize this data. So what we see here is the income and the wealth in one plot. I would like to discuss with you on which axis we should have income and on which axis we have wealth. Typically, on the x-axis, we have the independent variable that usually determines the dependent variable on the epsilon axis. But this is not so crystal clear here because the income could induce wealth. Because if I earn a lot of money, I'm able to save money and to become a wealthy man. Nevertheless, if I already have lots of wealth, I might also invest that money and earn a lot of income out of those investments. Accordingly, here, both directions are valid. Both hypotheses, like income determines wealth, as well as wealth determines income, both hypotheses are valid. So, we just saw that we can make hypothesis tests on correlations coefficients. Which hypothesis do we test here? None of them. Because the correlation just tells us about the co-behavior or about the interaction of two variables. But it does not at all support hypotheses that are directed into one direction. They do not test determination. They only test correlation. Later on, if we speak about OLS regression, logistic regression, logit models, or whatsoever, we will have determined hypotheses, but here we don't have. We have two-directed hypotheses. They only interact. There could be a third variable behind, just like the age determining both, or, just like I said, both variables kind of interact in both directions. That is also possible. But what we see now here in the plot is that there is seemingly some interaction, because if the income is high, just like at this point, the wealth seems to be high too. Or vice versa. If the wealth is high, the income will be high too. And if the income is low, the wealth is rather low, or vice versa. Wealth is low, income is rather low too. So that these points, these data points are, well, I don't know if they're really linear, if they're all on one line. But seemingly they are positively correlated. Otherwise, if they were negative correlated, the, let's say, cloud or the bunch of points here would be on this kind of diagonal. And if they were not correlated at all, they would be fuzzied around here, just like a ball or foggy in a foggy version. Well, what's the next step now? I just would like to shift the coordinates of this scatter plot in a way that we see the coordinates here instead of here. Why that? These lines represent the arithmetic means of those two variables. I don't know if you remember, the arithmetic mean of the income here is some 47,222, something like that. Accordingly here, 47,222 is given here and represented by this line. So I have shifted the coordinates to this point. What is this point? It's the balance point of this cloud of points. The balance point is just the point that you can balance an object just like this. So the point where all the arithmetic means intercept are the balance point of this. I just show you what that is for. Here I have the formula for the covariance. So the covariance is the arithmetic mean. That's why we divide 1 by n by the number of observations. And we sum up all this. So it's an arithmetic mean if we sum up several elements and we divide by the number of elements. It's an arithmetic mean. But what are those two brackets for? What are they for? Let's take a look into those brackets. In this bracket, we see each individual data point, or let's say the x value of each individual data point, minus the arithmetic mean of all data points. So, where do we find in the picture this bracket here? We find it here. For this data point, as an example, this line between the new axis, representing the arithmetic mean, and the data point, this distance is exactly this bracket here. The other bracket, the epsilon value of the same data point, minus the arithmetic mean, is exactly this distance between the point and the arithmetic mean, so the new axis. So inside those brackets, it's just a shift of the coordinates to where the balance point is. And now both brackets will be multiplied. So this distance times this distance will give, I just show you by drawing, will give exactly this area here. So this is very, very important to understand, that we're just calculating this area by multiplying those two terms, those two brackets. Now, let's see what happens to other points. I just show you. So these are not real data points, but let us assume that these data points would exist. A data point that is very close to this new epsilon axis would have a rather small area because, well, the one distance is very short. The other distance is long, nevertheless, this distance is very short. Accordingly, the area is very small. Another point that is close to the new x-axis will also deliver a very small area because, well, this distance is rather small, while this one is long, this one is small. Only those points that are somewhere in the middle between those axes will deliver quite a high or quite a large area into this. These areas are all defined positively. That sounds a bit curious because what area can be negative? Well, let's have a look. One down there. Because here, of course, this distance is a positive one. We take the x value, which is larger, minus the arithmetic mean, which is smaller, but this distance is negative because the arithmetic mean is larger than the epsilon value. Accordingly, we multiply a positive bracket with a negative bracket. And this area here, this box, has a negative area. Now we see that all points being in this quarter of the scatter plot have negative values. These one have negative values too. These one have positive values, and these one have positive values. The closer they are to the axis, the smaller is their area, the smaller is their weight inside the arithmetic mean. The far away from the axis they are, the higher is their weight. Accordingly, if we have most of those points close to this, let's say, hypothetical diagonal here, the larger will be the covariance. Vice versa, just imagine we had a line like this going diagonally down. Points being close to that would induce negative values. They would be negatively correlated. So that's the covariance. The only problem with the covariance is that we have, in this example, the income in euro on the x-axis and the wealth in euro on the epsilon axis. Accordingly, our unit is euro squared, and we have quite large numbers. So the covariance probably is a bit hard to interpret.
Please don't panic, just hand over all the money.
This is a lingerie shop, sir.
Some of you might have seen a different formula for the covariance in your textbooks. I just want to show you where this alternative formula comes from. So, if we take this basic idea that I've just introduced in this video, and we now multiply those two brackets, then we have 1 divided by n, the sum sign. I make my life easier and just write I, which means I across all n, or I counting from 1 to n. And now I can multiply out those two brackets, like xi times epsilon I minus xi times x epsilon bar minus x bar times epsilon, and so on. So the first one is xi times epsilon I. Now we have minus xi epsilon bar. We have minus x bar epsilon I, and plus, because minus times minus is plus, plus x bar and epsilon bar. So this is our first step. Now we see that we have lots of additions here, or subtractions, minus, minus, plus. So we have many terms that are summed up. We have a sum across several sums. And if we have something like that, of course we can sum in the other direction. That means we can distribute this sum sign to all those terms. I just do that. Of course I need some brackets then. 1 divided by n, I need brackets. And I sum across all I, xi epsilon I, minus, we have to keep the minus, but we now sum across all I, xi epsilon bar, minus the sum across all I, x bar epsilon I, and plus the sum, across all I. What's that? X bar epsilon bar, and closing brackets. All right. Now we need, of course, a little trick that I have already presented in another video. Nevertheless, I'm going to repeat that. It's about the properties of the sum sign. So let's keep it like that. I is counting from 1 to n, and we have something like a plus b. This is only an excursus, that's why I use different variables. Well, how can we handle this? We can handle this because let's split this into a and plus bxi. The sum is only connected to xi because I counts from 1 to n. The a is just another term and the b is only a coefficient. So the a is additively connected and the b is multiplicatively connected. Since a is a term on its own and we add n times a, we can also write 10 times a and get the a out of the sum sign just like that. I make my life easier again. Because this sum counts from 1 to n times a simple constant here, like a, we count n times a, so we can write n times a. And now the b is only a coefficient to xi. So we can take it out of the bracket or we can take it out of the sum sign, just like na plus b times the sum across all I, xi. Alright, so this was our excursus, and now we apply this knowledge to the formula at hand. So 1 divided by n, brackets, sum sign across all I. So here's nothing to do. xi epsilon I, that stays the same because both have an index. We can't take them out of the sum sign. But with the second term, we can take the epsilon bar out of the sum sign because it is multiplicatively connected, and we keep xi inside. Minus, this time we can take x bar out and leave epsilon I in. And here at the end, it is quite simple. We can take n times x bar times epsilon bar and closing brackets. So we can leave away the sum sign at all. And now we multiply out the brackets. So 1 divided by n times the first term times the second term. I just do that. 1 divided by n times the first term minus. And I put this epsilon bar in front. 1 divided by n, sum across all I, xi, minus, I put the x bar in front, sum across all I forgot the 1 divided by n, come on, and plus n times 1 divided by n, x bar, epsilon bar, and of course we already see that we can leave away both because that will be 1. Okay. Now, of course, we see that we have some kind of arithmetic mean here. We have 1 divided by n and the sum sign. That's always an indicator for calculating arithmetic means. So we have an arithmetic mean of the xi's times the epsilon i's. So we can rewrite this just like x epsilon bar. Again, here we have an arithmetic means, but we have to keep in mind the epsilon bar, and this is obviously the arithmetic mean across all x. So it is x bar. Don't mix this up. X epsilon bar is something different than epsilon bar times x bar. Okay, that's important to know. Minus x bar, and here's again an arithmetic mean of all epsilon. So here's epsilon bar and plus x bar epsilon bar. So seemingly we can leave away one of them because minus and plus the same. We can leave them out. Accordingly, the result is x times epsilon bar minus, we can switch those, x bar, epsilon bar is our final result, and this is the alternative formula for the covariance. If we now have understood the covariance, we need to find something that is more handy and better interpretable. And so we come to the idea of Pearson to normalize the covariance. And how can we achieve that? We divide by the standard deviation of x and by the standard deviation of epsilon, both multiplied. So here we see on the left, so under the square root, we see the variance of x together with the square root. It is the standard deviation of x times the standard deviation of epsilon. It can be shown quite easily that this is the maximum. Both together, multiplied both together, both standard deviations multiplied is the maximum covariance that can be achieved. So, dividing the real covariance by the maximum covariance will lead to a number that can be, at maximum, 1. Since the covariance can also be defined negative, it can also be -1. So the Pearson correlation coefficient is defined between -1, perfectly negatively correlated. They're all on one line going diagonal like this, or additionally positive 1. They're all on a line just like this. Written with the short writing here is we divide the covariance between x and epsilon by the standard deviation of x and the standard deviation of epsilon. And that's Pearson's correlation coefficient. Pearson's correlation coefficient, of course, has one large downside, one large disadvantage. Points that are far away from all the mean points here or all other points will get a very heavy weight in the covariance, in the mean here, because their area is so large that they can dominate the whole correlation coefficient. Accordingly, the Pearson correlation coefficient can be induced by only, or can be induced or can be dominated by only one observed point. Let us now take a look at the proposition of Spearman. Spearman does not correlate the pure values to each other, but the ranks. So what are the ranks? Here we see the income that is already sorted from the smallest to the highest income. So here we have the poorest guy, here we have the richest. Accordingly, the rank is 1, 2, 3, 4, 5. That's okay like this. The wealth, nevertheless, cannot be sorted too, because the values still have to stick to the individual. So here we have 20k, here we have 15k, here we have 13k. The poorest guy in terms of wealth is this one, so he will get the 1. The second poorest is this guy, so he will get the 2. So these are the ranks, just enumerated from the poorest to the richest in terms of income and in terms of wealth. Now, the Spearman correlation coefficient, the rank correlation coefficient, is defined just like Pearson, but based on the ranks. So here we see the covariance of the x ranks times the epsilon ranks. And here we see the standard deviation of the x ranks and here of the epsilon ranks. Or, written in brief terms, just like the same, the covariance of ranks divided by the standard deviation of ranks, rank x times rank epsilon. That's the idea of Spearman. And if we now replace this rich guy by an even richer with 1 million K income and 1 million K wealth, that one would really dominate Pearson correlation coefficient. Nevertheless, the rank would still be 9 and nothing else. So that's why the rank correlation coefficient is much more robust to outliers than the Pearson correlation coefficient. Thank you very much for watching this video, and see you in the next video, and don't forget to subscribe my channel.
Guys, what is this? Guys, all of you out right now.
Jared, I'm here to tell you that I'm quitting.
What?